Hello, welcome to this new lecture of Math-S400, Mathematics and Economic Modeling. Today we're going to see Kakutani's fixed point theorem, which is an extension of Brouwer's fixed point theorem, but then for correspondences. So if we start from a set S, which is a subset of Rk, and similar as to Brouwer's fixed point theorem, we will assume that S is compact, right? So it's closed and bounded and it's convex. Which means that if I take any two elements in S, then the convex combination of these two elements is also in S. So remember, for Brouwer's fixed point theorem, you had a function f from S to S, continuous. Well, in this case, Brouwer's fixed point theorem tells us that there exists some element x and s that's a fixed point, so f of x is equal to x. Okay, so Kakutani's fixed point theorem is very similar, but it doesn't work with functions, but with correspondences. Okay, so in particular, assume that we have a correspondence G, and now G takes an element in S and gives us output a subset of S. Okay, so G is a correspondence from S to S. Then Kakutani's fixed point theorem tells us that if this set is upper hemicontinuous, okay, so that's the first condition, and convex valued. Okay, so remember, convex valued means that for any x in the set, G of x is a convex set. Okay, and the last, a bit technical assumption, non-empty, which means that G of x is never empty. Okay, so if these three conditions are satisfied, then Kakutani tells us that G has a fixed point. In particular, it tells us that there exists an x and s such that x is in G of x. Okay, so here we had equality, right? Because this is an element in S and this is an element in S. Now correspondence gives you a subset of S. So here we use element-wise. Okay, so there's at least one x in S such that x is in its own mapping, G of x. Okay, so if I draw this here, okay, so here we, in two dimensions, here we have the set S and it maps to the set S. Okay, so we're looking for fixed points, which means that we're looking for points on this 45-degree line. And now I have an upper hemicontinuous correspondence that's non-empty and convex valued. So for example, something like this. You see it's upper hemicontinuous. It's convex valued, so for any fixed x, G of x is a convex set, and it's non-empty, so for every x at least there's something in G of x. And then Kakutani says that there's at least one fixed point. So in particular here there are many fixed points, so all the points on this line segment here are fixed points, right? So for example, this here, x star, G of x star is this part here. Alright, and you see that it contains x star on the diagonal. Okay, so this is Kakutani's fixed point theorem. It's a generalization of Brouwer's fixed point theorem, but now for correspondences and not for continuous functions. So let me show, maybe first by example, that each of these two conditions are actually important, right? So if you relax upper hemicontinuity or we relax convex valuedness, then we don't get necessarily a fixed point. Okay, so as a first example, we can take to do a dimensional case, right? So S is an interval and S is the same interval. We're looking for fixed points on the diagonal. And let me try to find a color here. So consider the following correspondence. So it's a line here, and then I include this point, but not this point. Okay. So let me call this correspondence here. This is my G. Okay, so you can see that G is convex valued, right? So for any x, G of x is a single point, right? So this is convex valued. However, it has a fixed point, right? So there's nothing on the diagonal that's also in the correspondence. So from Kakutani's 6-point theorem, you know that one of these assumptions should be cannot be satisfied. So in this case, it's upper hemicontinuity, right? So you can see because of this point here, this correspondence is not upper hemicontinuous. So we can find an example that doesn't have a fixed point and violates upper hemicontinuity. Okay. Now, to see that convex valuedness is also important, let me take a very similar example. So here we have from S to S, the 45-degree line. I'm going to take a correspondence that's very similar, except for one detail. Right now, this red point is included here, but not in the other one. And again, you see that G is a correspondence. It does not have a fixed point, right? There's nothing on the diagonal. However, in this case, G is indeed upper hemicontinuous. Okay, but the condition that's violated here is convexity. Why? Because, for example, at this point, both this point and this point are in G of x, but convex combinations of these 2 points is not in G of x. Okay, so only these 2 points constitute G of x. So G is not convex valued. Okay, so this shows indeed that both upper hemicontinuity and convex valuedness are necessary assumptions, right? If you try to relax one of them, you will have a violation of the fixed point property. Okay, so let's recall Kakutani's 6-point theorem. So you have G as a correspondence from S to S. S is compact and convex, right? So in particular, it's a subset of K, if you would forget. And G is upper hemicontinuous, convex valued, and non-empty. Okay. Well, if all these conditions are satisfied, well, then there exists some vector in S such that x is in G of x. Okay, so that's Kakutani's 6-point theorem. So we're not going to prove in detail this theorem, but we're going to give a broad outline of the proof of the theorem, right? So, and such that you get the idea of how to prove it. And I'm going to skip one detail, an important detail actually, but I will show you as we get along. So what's the idea behind the proof? So let's consider again the one-dimensional case. So we have S, some 45-degree line, and let's consider a correspondence, maybe something like this. Right, so here it's a single line, and then it opens up. Right, so this is the correspondence. So the idea behind the proof of Kakutani's 6-point theorem is to leverage on Brouwer's 6-point theorem. So here we can see that it's actually possible to use Brouwer's 6-point theorem in order to prove Kakutani's. So why is this? Because I can draw a continuous function, here I do it in green, that's actually always contained in the correspondence. Okay, so let me call this the function f. Okay, and so what do I have? I have that for all x in S, f of x is in G of x. Right, so for example here at this point this is f of x, right? And this is g of x. So we see that f of x is in g of x, right? And this holds for every point here. Okay. The second thing that I did when drawing this function is that I made f continuous. Okay. So what does this mean? Well, because f is continuous, I can use Brouwer's fixed point theorem, and I can show the existence of some element in S such that f of x is equal to x. Okay. However, I also have that for every x, f of x is in g of x. So in particular for this x here, I know that x is equal to f of x, right, because it's a fixed point. And I know that it's also an element in g of x. Okay. So this is equal to this, and there's an element of this. So this is an element of g of x, which means that x is a fixed point of g. Okay, so in particular, what we did is we tried to draw a continuous function that is in the always in the correspondence, right? Or is an element of the correspondence. And then we use Brouwer's, we find a fixed point, and then this fixed point would also be a fixed point of g. Okay, so what's the idea behind the proof? Well, the idea behind the proof is to find the function, or to get conditions such that we can draw a function f that's continuous and that's always contained in g. However, there's a bit of a problem when doing this in general. Okay, so let me give an example of a potential problem. So consider the correspondence. So let me draw the correspondence in red. Let me consider this one. Okay, and you can see actually that it satisfies a condition, it's convex valued, it's upper hemicontinuous, and there's a fixed point. In particular, this is a fixed point, this x here. Okay, so I want to prove that there's indeed a fixed point, so I will try to leverage this result. Okay, so I will try to draw a function f of x that's always contained in g of x and is continuous. Okay, so if I do this, so in this region, there's only one value of f of x that I can take, and I have to follow the correspondence here. I forgot to change to green. Okay, so here I have to follow the correspondence here. Also here in this part of the domain, I have to follow the correspondence. But here I have a problem, right? I have to jump from this point to this point, but I cannot do this in a continuous way. Right, so it's impossible to draw a continuous function that follows the vertical line here, because functions cannot be vertical, right? I can try to include this point and not include this point, but then f is not continuous, so f may not have a fixed point, which is indeed the case here. Right? So I have a very hard time for some cases to make this f continuous. So this is a problem, and the problem is going to be solved, and we're going to use the following structure or trick. Okay, so let me draw the example again. Okay, so here I have my domain, I have my correspondence that looks like this. So what is the idea? The idea is to, for each point in the correspondence, I will, for example, this one here, I will consider a ball of some radius epsilon around this point. Okay, and I will also do this for this point of the correspondence. I will do this for this point of the correspondence, for this point. I do this for every point in the correspondence. I will draw a ball of radius epsilon around this point for some epsilon bigger than 0. Okay, so I can keep doing this for every point, and I take the union of all these balls. Okay, so if I do this, I get something that will look like this. Alright, so intuitively what you can think of doing is blowing up this correspondence by an epsilon amount. Okay, so here the distance here, this distance will be epsilon. Alright, so you're going to make the correspondence thicker. Right? Now, once I have done this, I actually kind of solved my problem for this new correspondence. Right? So here it was impossible for me to draw a continuous function, but in some sense you can see that because I've now made it a gap between these two bounds. Okay, it's actually possible for me to draw a continuous function in this new correspondence. Okay, and now I have a continuous function, right? It's in this new inflated correspondence. It's not the original G, but it's the inflated G. But anyway, I can still draw a continuous correspondence, and it has a fixed point at some point. Let me call this x star. Okay. Now this is for some value of epsilon, for some inflation. Okay. So the idea is to do this, to find a fixed point, and then take a sequence of epsilons that decreases towards 0. Okay. So if epsilon is actually 0, I cannot draw this continuous function, but for any value of epsilon, I will be able to draw this kind of continuous function. So in any way, I will get a sequence of what you can call approximate fixed points. And then the idea is to use a limiting argument to show that subsequence of this sequence that converges, right, because the domain is compact, will actually converge to a fixed point of the correspondence. So this is the entire idea behind this proof, which we're now going to be to make a bit more formal. Okay, so let's take a jump into the bit more formal part of the proof. So what we're going to do is, first we're going to, for some epsilon, we're going to define this blown up correspondence. Okay. So actually what we're first going to do is this red thing here is the graph of the correspondence G, right? The red correspondence. So we're going to look at every combination of input and output of the correspondence that's epsilon close to some input output of the graph of G. Okay, and let me call this the ball of radius epsilon around graph of G. Okay, so this is basically what it is. So what's this? This is everything in this green thing here. So it's a value of x and it's a value of y. Okay, so it's an s times s. Okay, so because this maps from s to s, such that there exists, let me call it an x star and a y star in s times s, such that this is in the graph, right? Which means that y star is in G of x star. And if I look at the distance between this point and this point, it's smaller than epsilon. Okay, so you can say that x, y is in the ball of radius epsilon around x star, y star. Okay, so this is the same as saying that the distance between x and y and x star and y star is smaller than epsilon. Okay, so these two things are equivalent, if you remember this notation here. Okay, so what's this? This is the set of all x and y's, here in x and here y, such that I can find an x star and a y star that's epsilon close to this xy here. Okay, so if I draw a ball of radius epsilon around this, then I will hit the red curve, right? There will be something on the red graph correspondence, the red one here, that intersects this ball of radius epsilon around this point. Okay. So what's now the green correspondence? So let me call this G of epsilon of x. Well, it's simply y and s such that x and y is in this set here. Okay, p epsilon of graph of G. Okay, so this is now my new correspondence, which is this green one, which is epsilon an epsilon expanded version of the original graph of G. Okay. So the important thing is here that you understand all the real value of all this mathematical notation, right? That you understand what this sets mean and what this graph means. Okay. And now we're going to use a result that I'm not going to prove because it's quite elaborate. It will take several hours and several pages, I think. And that's called the von Neumann approximation theorem. Okay, so what does this result tell me? Well, this result tells me that there exists a function. So for all epsilon bigger than 0, there exists a function f, let me call this function f epsilon, right, because it depends on epsilon, that goes from s to s, and that's continuous, such that for all x and s, f epsilon of x is in g epsilon of x. Okay, so in principle it tells me that I can always find a function that's continuous and satisfies this condition as long as epsilon here is strictly bigger than 0. Alright, so for this expanded version, for the green one, I can always draw a continuous function in this correspondence. Okay, so this is the von Neumann approximation theorem. And here it's crucial that the correspondence is convex valued. Right? In order to prove this result, you really need convex valuedness of the correspondence. So here, this is where convex valuedness kicks in. All right, so given this result, because this function is continuous, well, I can use Brouwer. Okay, and I can find an element x and s such that x is an f of x, f epsilon of x, sorry, right? So the fixed point of this continuous function from s to s. And because this condition is satisfied, I know that this is g epsilon of x. Okay, so g epsilon has a fixed point. And this holds for every epsilon that's strictly bigger than 0. Okay, so for every expanded version of this g, I can find the fixed point of g. All right, so what do we have so far? So far that we have that for every x bigger than 0, there exists a fixed point of this g epsilon. So let me call this fixed point x epsilon, right? Because it may depend on epsilon. And s such that x epsilon is in g of x epsilon, right? So it's a fixed point of this blown up correspondence. So what's the idea? The idea is we're going to let epsilon go to 0, right? So we're going to take a sequence of epsilons that converges to 0. So as a first case, you can take epsilon equal to 1. Well, then there exists an x1 and s such that x1 is in g of x1. Can set epsilon equal to 1/2. Well, then I can find in x2 and s, right? Let me call this second fixed point x2, such that x2 is in g. So this should have been g1, right? Because this is the epsilon. g1/2 of x2. I can find take an epsilon equal to 1/3. Then again, I have a fixed point. Let me call this fixed point x3. I know that x3 is in g 1/3 of x3 and so on. Okay, so in general, for epsilon equal to 1 over n, I can find a fixed point. Let me call it xn. And because it's a fixed point, xn is in g 1 over n of xn. Okay. I can keep doing this indefinitely long, and in the end, what this gives me is a sequence of xn's in the domain, right? Everyone is in S, such that for all n, xn is in G 1 over n of xn. Okay. So let's go back. This is not the correct page. To this definition of G, right? So what's the definition of G? Well, it's all the elements y that are in x, y of the ball of radius epsilon around the graph of G, and then this is the definition of this, right? So given this here, then it follows that the point xn is in the graph, the ball of radius 1 over n of the graph of G. Okay, xy is in this thing here, and because x is equal to y for the fixed point, right? So we have xn. Okay, so this is just by definition that we have this. So by definition of this set here, what do we know? Well, we know that there exists, let me call this a yn star and an xn star, okay, such that this is in G. So in particular, yn star is in G of xn star, and the distance between xn and xn star yn star is 1 over n. Okay, so this is just restating this definition. Okay, so in particular we had a sequence. So here for this one, because this is G1, we can apply this definition. So we know that there is an x1 star and a y1 star, such that y1 star is in G of x1 star, and the distance between x1 and this thing here is smaller than 1. Okay, here we have an associated x2 and a y2 star. Here we have an x3 star and a y3 star, and so on, and in general an xn star and a yn star. Okay, so this is just to by application of this definition here. Okay, so let's recapitulate what we have. We had a sequence of xn's, so let me write them here in this order. I had x1, I had x2, I had xn, and so on. x1 is in G1 x1, x2 is in G1 half x2, x3 is in G1 third x3, and so on. And you have seen that using the definition of this G1 over n, we have this, right? So in particular, we have a sequence of xn stars and yn stars, such that yn star is in G of xn star, and xn is the distance 1 over n of xn star yn star. Okay, so we have an x1 star, an x2 star, and so on, xn star, and we also have a y1 star, y2 star, yn star. Okay, and all of these live in the set S. And this y1 star is in G of x1 star, y2 star is in G of x2 star, and so on. Yn star is in G of xn star. And the distance between these two goes to 0. The distance between these two, the first sequence and the third sequence, also goes to 0. So why is this? Because here xn is in the ball of radius 1 over n of xn star yn star. So if n goes to infinity, this sequence here goes to this sequence here. Right? So in particular, because these two are the same, we have that these two sequences converge to each other, and these two sequences converge to each other. So in the sense that let me write it here. We have that xn minus xn star converges to 0, and xn minus yn star also converges to 0. Okay, good. Now these are just sequences in S. Okay, so there's nothing to say that it will converge to anything. However, we can use the same trick as we have done over and over again, namely we use the Bolzano-Weierstrass theorem. And you can use it here because S is a compact set. Okay, so given this sequence here that lies in a compact set, we can find the convergent subsequence of these x's. Okay, so we have x phi 1, we have an x phi 2, in general an x phi n, and this subsequence converges, let's say, to some x. Okay, we can also take the corresponding subsequence of the x stars, x star phi 1, x star phi 2, and so on, x star phi n. And we can take the corresponding convergence of these sequences, y star phi 1, y star phi 2, y star phi n. Now this sequence converges to x, and this sequence here is a subsequence of the original one here that converged, whose distance to these first sequence converges to 0. So of course, if you take subsequences, you also have that x phi n minus x star phi n converges to 0, and x phi n minus y star phi n converges to 0. Okay, so given that these sequences converge to each other and this one converges to x, we have that this one also converges to x, and this one also converges to x, right? So all these sequences have to converge to the same limit. Okay, now we're almost done. We use a last property of Kakutani's fixed point theorem that we haven't used before, which is upper hemicontinuity. So here we have a sequence x star phi n that converges to this limit here, x, and for all n we have y star phi n let me rewrite it, right? So we have y star, you have sequence y star phi n that converges to the same x, and for all n y star phi n is in G of x star phi n. Okay, so this follows from the property that we have listed here. Okay, so we have a sequence of x's converging to x, we have a sequence of y's converging to something, and for every n the y is in G of the x's. Well, then we have upper hemicontinuity that says that the limiting of the y's, which is here x, is in G of the limiting of the x's, which is also here x. Okay, so x is in G of x, which means that x is a fixed point. Okay, so this is the part where we use upper hemicontinuity of the correspondence. Okay, so maybe good to go over the proof once more. So what's the idea? The idea is that we have a correspondence. We're going to blow it up a little bit by a factor epsilon, and then we're going to draw a continuous function in this correspondence to find the fixed point. All right, and then we're going to decrease the blow up bit by bit such that we have a sequence of fixed points, and then we're going to take a convergent subsequence of this sequence of fixed points to get our fixed point of the original correspondence. So here b epsilon of the graph is the blown up graph, and this is the blown up correspondence here. Okay, then we use the result that we haven't proven, right, von Neumann's approximation theorem, that shows that indeed there's a continuous function in this blown up correspondence, and by Brouwer we have seen that this continuous function has a fixed point. Okay, so for every epsilon, I can find an x such that x is in the blown up correspondence of x. Maybe I can get rid of these epsilons in order to avoid confusion. Right, so x is a fixed point of g epsilon. I can plug in different values of epsilon for a sequence going to 0. I get the sequence of x's that are fixed points of the corresponding smaller and smaller blown up of the original correspondence. All right, using the definition of this blown up correspondence, I see that there's points in the original correspondence that are very close to these fixed points, right? So in some sense they converge to the sequence. So we have a sequence of x's, we have a sequence of x stars, we have a sequence of y stars, the y stars and g of x stars. The difference between the elements in these two sequences converges to 0. The difference between the elements in the first and the third sequence converges to 0. Then we take a convergent subsequence of this first sequence, and if we do this, we find that these two other sequences, because they satisfy this property here, converge to the same limits. And then we simply use upper hemicontinuity of the correspondence G in order to show that indeed this limiting point is a fixed point of the correspondence.